Okay. Good afternoon. Today we will see some part which is remainder of chapter 3, that is data transmission element, and we will start chapter number 4. Therefore, data transmission elements. Data transmission elements. Name itself indicates that through these elements, data or information is transferred. When the measured variables have to be transmitted over long distances from the measuring points to a location for display or recording of data, data transmission elements are employed. These are also called telemetry units or systems and may be classified into two categories. First, landline or cable type transmission elements. Second, radio frequency RF type data transmission elements. In the former units, data is transmitted by wires or pipes, while in the latter, it is transmitted by radio waves. The former finds applications in data transmission in process plants, power generating stations, etc., and includes electrical, pneumatic, and position type elements, while the latter is used in aerospace systems. Now, first data transmission element we will see, that is electrical type data transmission elements. In these elements, the input measured variable, usually a motion signal, is made to change an electrical quantity, the effect of which is transmitted by wires to the receiving end for record or display. Figure 3.55 shows two such elements. In figure 3.55a, the position of contact C. This is the contact C, that this is the transmitter, this is the receiver. This is the position of contact, that is point C, on a variable resistance AB is adjusted by the input motion, changing the value of the current through the lines. The current at the receiving end is a measure of the input variable. In this type, resistance changes due to temperature changes introduce errors. In figure 3.55b, instead of measuring the current at the receiving end, a potentiometer is used. See that here at the receiving end, this is the potentiometer, which is balanced so that no current flows, as indicated by G. Thus, the setting of the potentiometer gives an indication of the input signal. In this case, the effect of change of line resistance due to temperature etc. is eliminated. Next is pneumatic type transmission elements. These are also called a landline type, or these are also landline type. A typical arrangement is shown in figure and uses the flapper nozzle arrangement. See that this is a flapper, this is a nozzle. The signal to be transmitted is converted into the form of a motion signal X. With change in X, pressure P2 changes as shown in the figure. Therefore, this pressure P2 will change. The pressure P2 gets transmitted to the receiving end and may, by use of an elastic element, be converted to motion for recording. Therefore, you just see here air supply pressure is there P1. Therefore, that supply pressure will, or that air will go to the nozzle also. Therefore, if you will adjust this flapper, if you will bring this flapper near to the nozzle, what will happen? There will be restriction to the flow of air outside the nozzle. Therefore, it will create back pressure, and this P2 pressure P2 will increase here. And when pressure P2 will increase, since this is the elastic diaphragm type of elements, they will expand and we will get the output. Similarly, if this flapper will move towards right side, pressure P2 will get decreased, and this diaphragm type element or this tube type element is there, it will get contracted. Means like this, motion will be there. Again, figure 3.57 shows a flow transmitter of the pneumatic type employing a system similar to that of figure 3.56. The flow signal results in a pressure difference across the restrictor which may be an orifice or venture or a nozzle. The pressure difference results in the deflection of an elastic diaphragm, and the motion signal is transmitted by being converted to the pressure signal P2 dash. These elements are not linear as shown in figure 3.56b. Therefore, again, this is the airflow. This is the restrictor. Airflow will go here. Therefore, what will happen? Again, because of this diaphragm will come down. When this diaphragm will come down, this lever will go up. Therefore, whatever the supply pressure, and here pressure P2 will decrease, and this is going to contract. Means same thing as that of the flapper. This thing here working will take place. Next, the input signal is in the form of a force signal F applied at the end of a pivoted lever. A motion input signal may be applied through a spring, resulting in force F. Application of F rotates the level clockwise as shown, decreasing the gap between the level extension and the nozzle, and thus increasing pressure P2 till the lever balances and no further building up of pressure occurs. At balance, P2 into A into D2 is equal to F into D1. A being the area of diaphragm as shown in the figure, and D1 and D2 the distances from the pivot. See that D1 D2 distances from the pivot. This is the force F which is applied at the end of the lever. P2 is linearly related to the input F. In pneumatic type transmitters, there is a pressure drop transmission piping resulting in a reduction in the signal transmitted. In practice, these are used for transmitting the signal over a few hundred meters. Force balance type pneumatic transmitter. Next is position type data transmission elements. In these types, the motion signal like rotation of a pointer is transmitted over long distances by use of synchros. Two synchros, a transmitter and a receiver, are employed. A synchro consists of a stator with three coils at 120 degrees, inside which a rotor which is free to rotate within the stator windings. The transmitting synchro is energized by an AC power source. If the two rotors are in identical positions, the voltages in stators have the same magnitude but opposite sense, and no current flows in the stator wires. If the input rotor is turned, making the two rotor positions different, current flows in the stator wires, producing a resulting torque which would align the two rotors, making theta 0 is equal to theta I. Thus, or theta output is equal to theta input. Thus, the angular position theta I is transmitted to the receiving end. Therefore, these two synchros are there. Theta I, it is transmitted to this theta O. When this will rotate, this rotor will rotate. Because of this rotation of the rotor, same motion is transmitted to this output rotor. This is synchro transmitter and this is synchro receiver. Next is radio frequency transmission system. Such data transmission systems use radio frequency waves for data transmission, and no wires or cables are needed between the transmitting and receiving ends. In large systems like aerospace systems, a number of input signals like temperature, pressure, vibrations, etc. may be transmitted by such units. Figure 3.60 shows such a radio frequency telemetry system. The transducer outputs are first modified by signal conditioners into suitable form and magnitude for each subcarrier oscillator SCO, whose output gets modulated due to the input signals. The frequency corresponding to each SCO is F1, F1, F2, etc. The outputs of subcarrier oscillators are mixed and then applied to a radio frequency oscillator for transmission. The signal is received by a suitable antenna at the receiving end, and after suitable demodulation and filtering, the original signals are recovered. Therefore, this is the end of the chapter 3. We will start chapter number 4 now. Okay. Next chapter. Chapter number 4. Force, torque and power measurement. Force measurement. In this chapter, various devices or transducers for measurement of force will be described. These devices are sometimes called load cells. Both static and dynamic force measurements will be considered, the latter including vibratory forces as well. The magnitude of the static or dynamic forces being considered may vary from a fraction of a Newton to several meganewtons, and thus special devices may be required, especially for extreme cases. For dynamic measurements, electromechanical transducers are often used. Calibration of such devices is an important feature which has to be carefully considered. The following types of devices will be discussed here. First, balance. Second, hydraulic load cells. Third, pneumatic load cells. And fourth, elastic type devices. Quite often in applications like machine tool dynamometers, wind tunnel testing, etc., the direction of resultant force to be measured is not known. In such cases, it is required to find the magnitude of force components. This may also include torque components along the three rectangular axes. Special techniques for such applications will also be discussed. Therefore, first is balance. Balance you are knowing. In Marathi, it is called as tarazu. This balance system we are using from long days since our childhood. Whenever we are going in market to purchase vegetables, whatever it is there, that shopkeeper is there. He is putting that weight in one pan and keeping that vegetables in another pan, and then it is balancing. Then whatever that amount of vegetable is there, he is giving it to us by paying the money. Therefore, this is known as lever system. A simple lever system shown in figure 4.1 called a balance has long been used as a force measuring device to measure the unknown force F at a distance L from the pivot. A mass M at a distance L from the pivot is used. The system is in equilibrium when FL is equal to mgl. With the knowledge of the other parameters, with length L, capital L and small l, mass M, and gravitational constant G, the force F can be calculated. Several versions of such balances are available for various force ranges and degrees of accuracy. Next is hydraulic load cell. In this type of device, hydraulic pressure is used to indicate the force F applied to a diaphragm or some other type of force transmitting element. When a force F is applied, see that this is the one cylinder or maybe one, we can say, rectangular box is there. In that this hydraulic fluid is there. Over the top of that, this diaphragm is there. Here maybe the load cell is there. When we will apply the force F, an unknown force F to this load cell, what will happen? This diaphragm will get deflected and this liquid will get compressed. When it is getting compressed, therefore pressure will increase, and that pressure is directly calibrated in terms of force F, and we are getting that unknown force value F. Therefore, when a force F is applied, pressure is developed in the fluid, which is normally an oil. This can be measured by a pressure indicating device like a Bourdon gauge. Such a device can be used up to very large forces of the order of millions of newtons. Next is pneumatic load cell. In this type of load cell shown in figure 4.3, air is supplied under pressure. See that this air is supplied under pressure at pressure P1. This is a constriction or restriction. And this air will enter inside this chamber. Is supplied under pressure to a chamber having a diaphragm at one end and nozzle at the other. See that this is diaphragm at one end, this nozzle at the other end. Application of force to the diaphragm deforms. First of all, we can apply the force here. This diaphragm will deform like this. Deforms it and changes the gap between the extension of the diaphragm and the nozzle, thus changing the pressure in the chamber. If the force F increases, the gap reduces, and this increase pressure P2 in the chamber. Therefore, if force F will increase, gap will reduce, and this pressure P2 inside the chamber will increase. This increase in pressure produces a force tending to return the diaphragm to its original position. Therefore, this because of increasing pressure P2, what will happen? It will force this diaphragm to its original position. For any force F, the system attains equilibrium and pressure P2 gives an indication of the force F. This type of the load cell is used up to 20 kilonewton. Now next is the elastic force devices. These are important devices for the measurement of both static and dynamic forces. In such devices, the force applied to the elastic member results in a displacement or strain in the elastic member, which is sensed by mechanical or electromechanical means. The elastic members may be in the form of rings, diaphragms, strips, cylinders, etc. Relations between strain and stiffness for some of the members are given here. Therefore, this is axially loaded elastic member. For the member shown in figure 4.4, strain E in axial direction and stiffness K in the same direction R. Therefore, strain, this is epsilon, means this is change in, this is stress divided by Young's modulus. This is strain, epsilon is equal to strain is equal to force divided by area into Young's modulus of elasticity. And K means stiffness, K is equal to EA divided by L. E means Young's modulus of elasticity, A means area, L means length. Where P is the force, is the Young's modulus, A is the cross section, area of cross section, and L is the length of the member. Therefore, this is first is the axially loaded member, means we can apply the force axially. Next is this is cantilever type of member. This is cantilever beam of length L, thickness T, and breadth B. When a force P is applied, therefore we are getting the deflection of the cantilever beam. Cantilever type elastic member, strain epsilon at the root of the cantilever is given by epsilon is equal to 6 PL divided by EBT square, and stiffness K is equal to force divided by deflection at the free end. Therefore, EBT cube is divided by 4L cube. Next, next is ring type elastic member. Due to the forces V and H means vertical force and horizontal force. Strain epsilon at theta is equal to 90 degree is given by epsilon 90 degree is equal to 1.09 VR divided by EBT square. Further, theta is equal to 39.6 degree. Therefore, at epsilon 39.6 degree is equal to 2.31 HR divided by EBT square, where R is equal to mean radius of the ring. Delta V is equal to 9.42 VR cube divided by EBT cube, and delta V is equal to 1.79 HR cube divided by EBT cube. In order to prevent rolling of the ring due to force H, an octagonal type ring as shown in figure 4.6 is used. In such a case, the strain theta is equal to 90 degree is only due to force V, while at theta is equal to 50 degree is only due to force H. Next is the mechanical method. This is the proving ring. See that when force P is applied on both sides, it will deflect and this dial gauge will indicate pressure. In order to measure the deflection of the elastic element due to the applied force, a mechanical method involving the use of a dial gauge may be used as shown in figure 4.8. The elastic ring called proving ring has on its inside an accurate dial gauge that can be calibrated in terms of the force. Different proving rings are available for various force ranges. Therefore, today we will see this force measurement only. Now, last method is nothing but electromechanical methods. For measuring displacement of strain, these methods use electromechanical transducers. Electromechanical means electrical and mechanical, that is mechanical displacement is converted into electrical displacement, electrical output. A piezoelectric transducer employing piezoelectric crystal is a useful device for dynamic force measurement. Such transducers are very sensitive and can be used for measurement of forces over a wide range of values. Figure 4.8 shows an LVDT type of force transducer for force measurement. The deflection of the elastic diaphragm due to force P is measured by a linear variable differential transducer. This type of device can be used for static as well as dynamic force measurements. Figures 4.9 to 4.11 illustrate the use of resistance strain gauges for force measurement. Figure 4.9 shows a cantilever type load cell with 4 strain gauges bonded at the root such that strains in R1 and R3 are opposite in nature to those in R2 and R4. In figure 4.10, the resistance gauges are bonded on the inside and outside of an elastic ring, which is ring type load cell. In figure 4.11, a hollow cylinder is loaded in axial direction, inducing both longitudinal and circumferential strains. R2 and R4 measure longitudinal strains, while R1 and R3 measure circumferential strains. The gauge arrangement has been shown with adjacent arms in the Wheatstone bridge having strains of opposite nature. Therefore, this is a LVDT type of force transducer. Already we are knowing this is primary coil, this is two secondary coil S1, S2. This is the iron core. When force P is applied, what will happen? This iron core will move in downward direction and the voltage induced in the secondary depends upon the amount of portion in front, amount of that iron core portion in front of the secondary windings S1 and S2. Similarly, this is cantilever type load cell. This is cantilever beam. This R1, R2, R3, R4 forms the 4 resistances of the Wheatstone bridge. When force P is applied, there will be change in resistance of either R1 or R2 or R3 or R4. Therefore, we are getting the deflection in the galvanometer and we are getting the actual reading of the force. Therefore, again, this is ring type of cell. See that 4 resistances R1, R2, R3, R4, and this is cylindrical type of cell. R1 opposite to that R3, this is R2, R4. Therefore, today we'll stop here and next lecture we'll take torque measurement.